No problem.
Okay, so our speaker today is Jack Kelly, whose title is that you see there, Bornological Spectra and Bounded Cohomology. Please, Jack, go ahead.
Thanks very much for having me. So yeah, so as Guillermo said, I'll be talking about Bornological spectra and bounded cohomology, and this is sort of a work in progress. A little list of the a few of the bits I say at the end will be a little bit speculative, but yes, so my this is sort of quite a big project, and the collaborators in this include Federico Bambozzi, Oren Ben-Bassat, Kobi Kremnizer, and Devarshi, who I guess many of you know. So I'll start with a bit of motivation, and this sort of Bornological spectra, it's a subset of a bigger project to sort of develop a notion of derived analytic geometry. So I've got a work in progress with Oren and Kobi developing analytic geometry over some Banach ring. It's geometry relative to some symmetric monoidal category. And eventually we hope to sort of include some sort of analytic geometry over the sphere spectrum, whatever that means, using some sort of Bornological spectral technique. So I'll just recall very briefly some very basic motivation from sort of algebraic spectral geometry. So spectral algebraic geometry is geometry relative to this, in the sense of Johnson and Trauber, this HA context of symmetric spectra, or i.e. the stable homotopy category. So just as derived algebraic geometry is sort of geometry relative to the category of simplicial modules over your ring, spectral geometry is geometry relative to the monoidal category of symmetric spectra. And in this notion of geometry, affine objects are sort of multiplicative cohomology theories. And they're useful in that they include things like, in particular, elliptic cohomology theories, and these geometric techniques allow you to build some sort of more sophisticated things like topological modular forms, which you can construct as some sort of global sections on some geometric object in this context. And ultimately, we would like to be able to do something similar in analytic geometry.
Sorry. Yeah. What? So I'm used to HA meaning.
Oh, sorry, it's
analytic homology. So this is realistic. Yeah.
Oh yes, so a HA context. Sorry, yeah, it's like a homotopical algebra context.
Okay.
And it's the setting of Johann and Trauber stuff. So it's a really ultimately you're interested in the infinity category, but it's a model category which satisfies a bunch of monoidal model category, which satisfies a bunch of nice properties. Yeah. So yeah, as I say, this spectral geometry, analytic geometry is ultimately going to be related to this notion of derived analytic geometry. So okay. Let me explain a bit of this idea for analytic geometry as relative geometry. So the idea is sort of quite simple. So I guess very familiar in algebraic geometry, the idea, this sort of functor points approach to algebraic geometry is that a space should be locally determined by its algebra of functions. And in analytic geometry, something kind of similar happens. At least the finite dimensional Stein complex or ridge analytic space, the geometry is determined locally by the algebra of functions once you take into account this sort of extra topological structure you have on it. So in complex analytic geometry, you'll have Stein spaces, or so that which holomorphic functions, and those will be Frechet algebras. And in ridge analytic geometry, you'll have Tate algebras, which are Banach algebras. So the sort of zeroth approximation is that analytic geometry should be geometry relative to the monoidal category of Frechet spaces. I guess so. Yeah, this sort of relative approach to geometry, you start with some monoidal category, you look at commutative algebra objects in this category, and your affines you just define to be the opposite category to this, and then you look at some topologies on this and stacks, etc. And so the zeroth approximation is that you do this relative to the monoidal category of Frechet spaces, but there's a bit of a problem here, and the problem is that this category is quite terrible. So if, for example, it doesn't have limits, most limits and colimits, it's not closed symmetric monoidal, the tensor product doesn't have a right adjoint, you don't have an internal hom. And in terms of derived categories, so Frechet spaces do have some sort of homological structure. It is a quasi-Abelian category, but it's not a very good one. So it doesn't have enough projectives, doesn't really have compact projective objects at all. So for technical reasons, you instead embed it into this bigger category. So there's a way of embedding it into this sort of category of Bornological spaces. So formally, this is defined to be like monomorphic inductive limits of Banach spaces, sort of very formal category, which you can realize it as like it's a concrete category. So it's a
so the M is for monomorphisms.
Yeah. So the M means monomorphism. Yeah. You can remove the M and work with in-ban. Homologically, they're the same. They have equivalent derived categories. But this complete Bornological spaces is a concrete category, so it's just a bit nicer, I guess, to get your head around. And the nice thing also is that you can K here can be any Banach ring, so it can be C, it can be any non-Archimedean Banach field, but it can also be the Banach ring of integers, which is just sort of the integers with this Euclidean norm. You just restrict the norm on R. This is a Banach ring, and this allows you to do geometry relative to this. So you get sort of just like universal geometry. Yeah. So I'm not going to go into the details of this sort of derived analytic geometry. This is just sort of why I'm considering this category of Bornological spaces. And in fact, for the purpose of this talk, I'm going to be more interested in a bigger category. This half means semi-normed here. So it's the category of sort of neither complete nor separated Bornological modules. Did I know? Yes, so I forgot to put the definition, but this is int M of I replace span here by semi-normed K modules. So the norm is not complete or separated. Yeah. So again, this is not abelian, but it is quasi-abelian. So any quasi-abelian category has two T structures. In particular, the one would be interested in the so-called left one. It's the heart of this T structure is called the left heart, and you have this very nice property that you get an adjunction, which the right adjoint is exact, and moreover, you get an induced equivalence of derived categories. So at least up to homotopy, these two categories are the same. Yeah, and that's nice because, well, the left-hand one is abelian. And in fact, it's more than abelian. It's called a monoidal elementary abelian category, and all that means is it has compact projective generators. The compact projective generators are closed when you're taking tensor products, and they're in fact closed when they're taking symmetric powers. And all this data just wraps up into the fact that this does, if I look at simplicial objects in here, I get a HA context.
Sorry, is there I mean, can you give an idea what the objects in LH are?
So yeah, if I have any quasi-abelian category, the left heart can be sort of described as the sort of two-term complexes of objects in the quasi-abelian category, where the only non-zero map in the complex is a monomorphism, but the monomorphism isn't necessarily strict. And then, yeah, this left adjoint just sort of takes the quotient, and the right adjoint just includes it as the complex where one of the term, everything is zero except in degree zero.
So there are no nicety of no nice properties of the Bornologies are required. Just it's a formal thing that
yeah.
It's in equation. Okay.
Yeah. And it's very formal, as I'll show in a second or explain in a second. So yeah, this fact that it's monoidal elementary, etc., means that it's a good setting for derived algebraic geometry or relative derived algebraic geometry. And you can give a description of the compact projective generators. I'll explain in more detail what this is later, but this is sort of if I take any normed set, a normed set is just a set equipped with the function to the non-negative real numbers. this L1 of here is I take the free abelian group on this, and the norm, I just add up the norms of everything in a sequence. So this is sort of like a non-complete. So L1 will usually mean the Banach space. This is sort of a non-complete version of this. Yeah. And because you have all these compact projective generators, some general nonsense means that this category, this left heart, is what's called the free sifted co-completion of the full subcategory on these projective objects. So the free co-completion by sifted co-limits, which is, I guess, essentially a combination of filtered co-limits and reflexive co-equalizers. Okay, so yeah, the most important thing, sort of strangely, to take from this is this equivalence here, because this is what's going to show up later when I want to define Bornological spectra. Okay, so yeah, I guess before attempting to define Bornological spectra, I'll just recall a bit about classical spectra. And I guess classical spectra are some way of encoding generalized cohomology theories. So just to recall quickly what a generalized cohomology theory is, it's just a pair which assigns to any, I guess these should be pointed CW complexes. So it's a functor, H star here is a functor from the category of pointed CW complexes to graded abelian groups. And delta is some assignment of maps to this shift, and these should be natural in some obvious way. And you want to satisfy these four familiar properties. So it should be homotopy invariant, homotopic maps induce the same map on cohomology. You want this exactness where, yeah, this map here is this, and this map is from collapsing A to the point. And you want this excision property. So I can, if X is a union of some subcomplexes, I can sort of, the cohomology of X relative to B is the same as the cohomology of A relative to the intersection. And the last thing is just this additivity property. Something to do with cohomology of the disjoint union is the product of the cohomologies.
No cardinality restrictions.
Sorry?
There are no cardinality restrictions on the number of elements that.
No, I think so. No. Yeah, because ultimately it'll just be, something, when you represent them in terms of spectra, it'll end up just being, it transforms it'll be some mapping space with a co-limit in the left, it goes to a product outside of it. These generalized cohomology theories, they can be realized as basically as they're representable in a precise sense by so-called spectra, which are objects of some stable category. So I'm just going to recall, give a sort of brief overview of constructing stable categories, because I'll need the more general construction later. The familiar category of spectra is the stabilization of the category of pointed topological spaces, and everything here is an infinity category. You don't need to really worry too much about the precise details of infinity categories, and in fact, all the ones I talk about will be presentable by model categories anyway. But talking about infinity categories just lets me sort of gloss over the technical annoyances of model categories. And if I start with any at least presentable, you need less than presentable, but everything here will be presentable anyway. Presentable infinity category. The stabilization can be defined as this homotopy limit of this tower of C, where I keep applying the loop space functor. And informally, and if you talk about model categories, you can make this precise. Informally, an object consists of tuples. So you have such sort of you're sort of adding the negative bits basically. So you have a map from the suspension of Cn -1 to Cn, and I require that the adjoint map, so sorry, sigma here is the left adjoint to omega. You put a push out here rather than a fiber product. I require that on the map on from Cn to the loop space is an equivalence. And this is a stable category, i.e. the sigma and omega are inverse to each other in this category, because if you compute it, so yeah, you can usually write an object just as a sequence, and all sigma does is sort of shift everything to the left, and omega you just apply term-wise, and because of this equivalence, you see that this is sort of an autoequivalence. So this is a stable category. Yeah, so any stable category, stable categories are sort of the infinity enrichment of triangulated categories. So the homotopy category is triangulated. Yeah, and you have this sort of infinite de-looping functor from the stabilization back to C. It just sends this sequence to C0. And C0 here is sort of an infinite loop space because it's omega C1, omega squared of C2, etc. So you denote it by this sort of infinite loop space functor. This thing has a left adjoint. For presentable, it sort of has a left adjoint by formal nonsense by some adjoint functor theorem, but you can explicitly describe it like this, at least if you're careful about working with model categories. And it also has a T structure. I guess this is sort of general theorem of Lurie, but you can at least describe the negative part quite easily. Something is in the negative part if this infinite de-looping is trivial in the original category. And the non-negative part is slightly more complicated, but it's sort of the part generated by this infinite suspension functor. So it's sort of the part generated by C when I map it into the stabilization. And this, you can check, does define a T structure. And if I take the category of pointed topological spaces, the heart is a category of abelian groups. This is not immediately obvious, but I guess the sort of way you realize it is the functor from the abelian groups to the heart is given by Eilenberg-Maclane spectra, and you can prove that this is an equivalence. And if I take a pointed topological space, if I look at the homology functors for this T structure, and I apply them to this suspension, I get the usual stable homotopy groups of X. Okay. And yeah, so the statement I want to come to is Brown representability. So if I take any object of this stable category, I guess I should have, yeah, under some assumptions at least, if C is Cartesian closed and the product commutes with finite coproducts, you get a closed monoidal structure on this stabilization. So I can define this sort of homology theory by applying the homology functors for the T structure to the fiber of this map here. And so this, if the non-negative part is closed under products, then this determines a sort of C-valued generalized cohomology theory. What I mean is that all of the axioms of a homology theory are satisfied where you replace, like, excision should be something to do about homotopy pushouts. Yeah, so this gives me the final one about the additivity axiom. And so I'm not going to go through the proof of Brown representability theorem, but if all generalized cohomology theories on topological spaces arise in this way, so every generalized cohomology theory on pointed topological spaces can be represented in this way by some spectrum. And I guess one thing I want to point out is how, so yeah, I guess all the axioms for being a generalized cohomology theory are just formal nonsense, basically. In particular, the excision axiom. So for excision, what you have, at least for spaces, is you have some homotopy pushout, and then I apply some mapping space. Just again, with formal nonsense, mapping space will send homotopy pushout to a homotopy pullback. in a homotopy pullback, the fiber of this map will be equivalent to the fiber of this map. What this precisely says gives you excision. It's precisely the statement of excision. Yeah, okay. So as I say, all, at least for topological spaces, all generalized cohomology theories arise in this way. But there's a not quite cohomology theory that people consider, which you can't realize in this way, which is bounded cohomology. So bounded cohomology, as you see, it's not super tricky to define, but it turns out to be extremely difficult to compute. So it is a homotopy invariant of spaces, and it was introduced to study things called simplicial volumes in differential geometry. So if I start with a CW complex, I just consider the set of n simplices in X, so continuous maps from the topological n simplex into X. And I can regard this as a semi-norm set in sort of a stupid way. I just declare the norm of every element in this to be 1. And then I can define this sort of space of bounded cochains as bounded maps from this norm set into R, where here R is just equipped with the usual Euclidean norm. And then the bounded cohomology is just the cohomology of this complex. And then you can define the relative bounded cohomology in the usual way. It's the cohomology of the kernel. Sorry, there should be an A here on the right. This construction is functorial, so I get a map from bounded cochains in X to bounded cochains in A, and I look at the cohomology of the kernel. So this functor, it satisfies axioms 1, 2, and 4 being a generalized cohomology theory, but for reasons I'm not going to go through, I don't fully understand the details. They're very, it's very differential geometry heavy proof. It does not satisfy 3, and I think the standard example is something like the bounded cohomology of the circle for n bigger than or equal to 1, it's all 0, but the bounded cohomology of the wedge of 2 circles in H2, it's generated by, it's got infinitely many generators or something like this. So in particular, you don't have a Meyer-Vittori sequence, and so you can't have excision. So you don't have excision for this theory. And the idea is that this, we're computing it in the wrong category. So what if, I'm going to sort of refine the definition to incorporate the quasi-abelian structure that's sort of hanging around here. So the space of bounded cochains has a natural semi-norm structure, as I mentioned, and it's in fact a Banach structure. And the norm, since everything is norm 1 in Sn of X, the norm of an element is just this straightforward thing here. So I can regard the category of semi-norm spaces as a full subcategory of Bornological spaces. And I'm going to define Bornological bounded cohomology to be, so these functors here, by this I mean the homology functors for the left heart. So I'm going to keep track of the Bornological structure on these complexes. Technically, so I said you have to, so this fiber here, I'm taking sort of a derived fiber. This is a fiber in some infinity category. You only need that. Well, I guess you can replace R here by any Banach algebra and do the same, play the same game. For R, this map here is actually a strict epimorphism, so you don't. It's just the usual kernel. So for normal bounded cohomology, this is just the kernel. You don't have to derive anything. And the claim, which is almost a theorem, is that this satisfies excision in this sort of Bornologically enriched way. You have this, once I take into account the Bornological structure and I make sure I'm working in the left heart, I get this isomorphism of relative bounded cohomology. And the idea, you can prove it directly without worrying about Bornological spectra, but sort of the most conceptual way of proving it is that it'll be represented by some kind of Bornological Eilenberg-Maclane spectrum. So that's the hope anyway. Okay. So yeah, I guess I'm going to try and define some notion of Bornological spectra now. So I guess I should explain kind of what I mean by Bornological spectra. Like what is the kind of structure that I'm interested in? Well, sort of roughly speaking, it should be some category of spaces whose homotopic groups naturally have some Bornological structure. And these spaces should be equivalent, or a map of these spaces should be equivalent if they induce isomorphisms on these Bornologically enriched homotopy groups. So really, I'm looking for something which is a stable category with the left and right complete T structure, and the heart of this tree structure should be the left heart of Bornological modules, or Bornological abelian groups, I guess. And okay, so the sort of very rough way of thinking about it is the category of spectra is the stabilization of the category of pointed topological spaces. The category of pointed topological spaces is equivalently the free sifted co-completion of the category of finite pointed sets. It's important this is an infinity categorical co-completion. The point here is that sort of once you can do suspensions, you can sort of get everything. Suspensions and disjoint unions, and a suspension is a homotopy push out along a point, or like 2 points going to 1 point, basically. So this gives me all topological spaces, and the functor to the heart, so the pi0 functor for the stable structure, it sends one of these finite pointed spaces to the free abelian group on this object. And it sends this sort of free sifted co-completion to the free sifted co-completion of free abelian groups of finite rank, which is just the category of abelian groups. So on the right-hand side, I want to replace free abelian groups of finite rank by sort of this L1 construction on a normed set, which is the left heart of Bornological spaces. And I have to figure out what I want to put here. And the idea is that this L1 of V should be some kind of free semi-normed abelian group on this semi-normed set. And so the first thing I'm going to try is I'm going to try replacing finite pointed sets by normed sets. So I guess I should formally define what a normed set is. Oh, sorry. So a semi-normed pointed set is just a sort of stupid thing. It's a pointed set equipped with a function to the non-negative real numbers, which sends the point to 0. I can define what it means to be normed just by saying the only thing it sends to 0 is the point. You define bounded maps of these things in the obvious way, the same way as you define bounded maps of Banach spaces, just there's some bound on how big f of x can get. And these obviously arrange into some category. This F1 notation just comes from one of the original papers on this. Yes, I guess it's a bit of an affectation. It's just, I guess one of the sort of notions of modules over F1 is pointed sets. And so now these are just sort of normed modules over F1. And you can define the sort of normed category in the obvious way. And you can prove that both of these categories are Cartesian closed, symmetric monoidal categories. Yeah, and now I can finally define this thing. So if I take a pointed semi-normed set, this L1 is a free abelian group, and the semi-norm is just I add up all the norms of V with this weight coming from the element of the tuple. Okay. Yeah. So yeah. I want to sort of construct some spaces based on these things. I'll talk about something a bit more general first. So, and this will be sort of the leading up to the non-stable category of Bornological spaces. And this is a very general construction. So if I start with any pointed one category, I can consider this like infinity categorical free stiff to co-completion, which is equivalently the category of functors which commute with finite products and from the opposite category into spaces. Yeah. And if I apply pi n, so for each c, if I have such a functor for each c, if I apply to c, I get some topological space, or pointed topological space even, and I apply pi n. Pi n commutes with finite products in spaces, so I actually get this functor here is a finite product preserving functor to set, so it determines an object of this free sifted co-completion of C. And in degree 1, this will be an abelian, or sorry, this will be a group object in this free sifted co-completion, and for n bigger than or equal to 2, it'll be an abelian group object. So, okay, this is a sort of a very formal thing, but you can realize it as a in a sort of, well, kind of concrete way. In particular, it's got a model category presentation. So if I take the one categorical free sifted co-completion of C, and I look at simplicial objects in here, this gives me a model category. The weak equivalences are determined by, for every C in C, I apply it termwise to my simplicial object. If it's a weak equivalence or a fibration of simplicial sets, that determines being a weak equivalence or a fibration of this free sifted co-completion. And this presents this infinity category. So you do have some sort of kind of concrete model. And because I've defined these homotopic groups, it's just I apply them after applying F, or applying mapping from C into this thing in each. It's clear then that a map in this category will be weak equivalence precisely of these homotopy groups or homotopy objects, taking values in the free sifted co-completion are isomorphic. So yeah, okay. And to get Spectra, I just stabilize this construction. So I take the stabilization of the free sifted co-completion of this thing. This may seem like an absurdly formal object, and as it'll turn out, it is actually far too formal. But I'll stay with it for the moment. So I can define, since I have these sort of homotopy objects, I can define, as I usually do for spaces, these stable homotopy objects. And again, by construction, a map of these spectra will be an equivalence if and only if, when I apply each of these stable homotopy groups, this becomes an isomorphism. And I would like these homotopy groups or homotopy group objects to be sort of the homology functors for some T structure on this category.
So sorry, just one little question.
Yeah.
I mean, your aim was to have some form of spectra whose stable homotopy groups had a bornological structure, natural bornological structure.
Yeah.
So is there any reason why we should expect that all this contraction will yield such a thing?
So
because I got lost in the middle of the construction, so that's why I'm asking for guidance. Right?
Yeah, sure. Yeah. So this is, I guess the idea is that I want to construct some category. I want it to be a nice category, presentable, et cetera, et cetera. So this is why this free sifted co-completion is a good thing. But also I want some T structure so that the left heart is this thing. It's the left heart of Bornological spaces, the free sifted co-completion on these guys. And the idea is I kind of regard these L1s, they should be kind of some free semi-normed abelian group on this semi-normed set. The problem is this is not quite correct. They're not free in a precise sense, or in the sense that you would like. So yeah, the idea is that, okay, for abelian groups, or for normal spectra, I look at finite pointed sets on the left-hand side. The free abelian group on a finite pointed set is your usual Zn or whatever. So this gives me abelian groups. I would like, say I put in here normed sets, free elliptic completion on normed sets. If this L1 were a free thing, it would give me complete Bornological modules. But it's
and so by some previous slide, the right-hand side of this pi zero thing is what?
It's the left heart.
Yeah.
Yeah.
What?
It's the left heart of Bornological modules.
Okay.
Yeah. So yeah, I guess I should have put the isomorphism in here. But yeah, as it turns out, as I'll explain briefly, this thing, if I take this like big free stabilization of the free elliptic completion of semi-norm things, it won't quite be this. It is far too formal an object, but it's going to be a localization of it. Yeah. Okay. Yeah. So yeah. Yeah. So I can define these. So yeah. The point is, I guess, yeah, I'll get to it in a second, but the point is that these abelian group objects in the free elliptic completion, this category is much bigger than sort of complete or Bornological abelian groups. It contains non-convex stuff, but yeah, I'll get to that in a moment. So yeah, by like some general theorem of Lurie, this category, as I mentioned before, it does have a T structure, and you can prove with a bit of effort, I won't go into that the homology functors for this T structure are these sort of stable homotopy group objects. To prove it, you need some kind of Freudenthal suspension theorem in this category of generalized spaces, which is ultimately some result of RESC. Yeah, I guess if I'm going to be completely precise about it, RESC has some version of this excision theorem for homotopy groups, which works in any infinity topos. And this free elliptic completion is, you can realize it as infinity topos. It's like infinity sheaves on some category. So just by some general hammers, like big powerful theorems, you can use these group objects I've defined are the homology functors for the T structure on this category of spectra. And you can use this to show, so yeah, as I've defined them, these functors, they're finite product preserving. So I get functors, they give me functors. So for each X, I get a finite product preserving functor from C up into abelian groups. This is equivalent to the category of abelian group objects in the free elliptic completion of C, or if you like, it's the free elliptic completion of free abelian group objects on elements of C. And then there's an Eilenberg-Maclane structure in this generality. You just do for any functor. So if I have an object in here, i.e. a functor from C to the category of abelian groups, I apply the Eilenberg-Maclane construction sort of term-wise, and this gives me an Eilenberg-Maclane functor in this very general category of spaces, and you can use this to show that you get an equivalence. So the heart of this T structure is abelian group objects in this big one categorical free elliptic completion. So now I apply this to the case of semi-normed sets. So yeah, I do this big construction, and the problem is that this category, the way I've constructed it is sort of obviously enormous, and it's far too big. So, for example, by the way semi-norm sets are defined, there's no, if I look at an abelian group object in semi-norm sets, there's no reason why this sort of additivity structure, it should be bounded by 1. So I get like non-convex objects in here, for example, and I get way more things than this, like the free abelian group objects are some big, huge formal construction. So this category is way too big. But it's not everything, all hope is lost. So sort of normed objects do sit inside here. There is a full subcategory where A is equal to 1. I consider that as a full subcategory. And so norm objects do sit fully faithfully in here, and I can extend by these monomorphic colimits, because this is a co-complete category. And it turns out that this guy sits fully faithfully inside the category of abelian group objects. And again, by some general nonsense, this just adjoint functor theorem, this functor has a left adjoint, which means that this category, the category I want is a localization of this category. And I sort of want to boost this localization from the heart to the level of spectra. And you do this using this construction using so-called Moore spectra. They're sort of quite peculiar objects. So for an element of my category C, I'm just going to define this sort of sphere spectrum on C to be the infinite suspension of C. And you can compute the zeroth homotopy group. It's the free abelian group object on C. You can compute this quite easily, actually. You use something like this Eilenberg-Maclane functor as a right adjoint to pi 0. And you just see that this thing satisfies a universal property using some adjunctions with sigma infinity and omega infinity. I sort of hoped that you compute pi n, it's the free abelian group on C tensored with pi n of the sphere spectrum, but I'm actually not sure that's true, but at least I know pi 0, and that's all I really need. And so then I can compute pi 0 of maps from between two of these objects, and just by running through a bunch of adjoints, pi 0 of maps between these objects is just homomorphisms of abelian group objects from the free object on C to the free object on C prime. In particular, any map of abelian group objects lifts to a map between these sphere spectra. But it's not functorial in any way. Even in, I think, yeah, even in for normal spectra, this basically I'm saying that this Moore construction is not functorial of the category of abelian group objects. And even for spectra, that's the case. So this isn't a functor. But nonetheless, if I take some abelian group object, I can pick some resolution by these free objects. And just by running up the chain, I can pick, I can construct some diagram of sphere spectra. I just inductively pick lifts of the maps. So that's fine, I'm allowed to do that. And I define the Moore spectrum to be the geometric realization of this object. And although this Moore spectrum function, Moore spectrum, it's not a functorial construction, at least at the level of infinity categories, you can show that it is when you pass to the homotopy categories. In particular, I've got a well-defined map, at least in the homotopy category, from the free abelian group object on V to L1 of V. Yeah, so I've got a map from V to L1 of V. So I've got a map from SC. So yeah, at least in the homotopy category, just by universal properties, I do get this map. And I define my category of Bornological modules to be the localization of this category of this big, huge category at maps of the, I want to localize it this map, so I want to invert these maps basically. To make this a stable localization, you also have to invert shifts of these maps. And now, this basically does give me the localization that I wanted. So if I have some object of this category of Bornological spectra, Just by definition, this sort of stable localization, the nth stable homotopy group of this, just by definition of the homotopy group, I can define it as the nth stable homotopy group of this mapping spectrum. But since I've localized the maps from M of the sphere spectrum to M of this L1 object, this map here is an equivalence. So I get a product preserving functor from L1 of this category of projective generators to abelian groups. Because to the homotopy category, at least, this more spectrum functor does send coproducts to products. You can just see that just from how you compute resolutions. So it does determine an object. Sorry, this should be the left part. So this, if I have objects in this like localization, then I can regard the stable homotopy groups as existing in this full subcategory of this huge free cyclical completion consisting of Bornological objects. And this is the category that I want. And you can also define complete Bornological spectra. You replace L1 of V with the actual separated completion. And that gives you complete objects. So now, with that all defined, how do I get back to bounded cohomology? So I want to at least, I want normal spectra to sort of live inside here. And that's kind of easy. So if I consider, as I mentioned before, this from the category of pointed sets to the category of pointed norm sets, I just equip every element of the set with the semi-norm whose value everywhere away from the marked point is 1. And this is the fully faithful functor. And there's an induced functor on simplicial objects. I just do it level-wise. And you can prove directly that this functor commutes with push-outs along monomorphisms. It's just because it commutes with disjoint unions. And push-out along monomorphism is essentially taking disjoint unions. And also preserves homotopy equivalences between fibrant objects. And that's just because it'll send the sort of one simplex in pointed simplicial sets to the one simplex in pointed norm sets. So if I have an equivalence between fibrant and cofibrant objects, this will just be a homotopy equivalence. And so I get a homotopy equivalence after applying this functor. And all this together means that this functor preserves, preserves homotopy equivalences. Cofibrations in this thing are actually just what are called admissible monomorphisms, but it does preserve such things. And a sort of easy argument then implies that this functor commutes with homotopy pushouts. So if I then define, this shouldn't be a pair, just for any X, a CW complex, I can define this sort of Bornological bounded cohomology to be the cohomology. So if I take R to be the Banach abelian group, just with its usual Banach structure, I do this Eilenberg-Maclane's construction for Bornological spectra. And then if you compute it, it's very straightforward to compute. This Bornological bounded cohomology I defined earlier is just the cohomology of the mapping spectrum, i.e. the Bornological bounded cohomology is representable by a Bornological spectrum, just a sort of straightforward Eilenberg-Maclane spectrum. And so you get excision just in this general nonsense way. Yes, okay, I guess I will stop there.
Okay, thank you very much. I mean, do you know, I mean, once you have excision, right, if you know what the homology is on a point, say, then you can compute, I suppose. And the point gives this what? So I suppose this is determined by K of R, right?
Yeah, so I think what happens if you compute it for the sort of Bornological circle or whatever, you get in this sort of big category of freely abelian group objects, I think what you just get is sort of the free abelian group object on the point, which will be the constant functor with value z. And then when you localize this, I think you should get the Euclidean integers. Now, okay, what I'm not certain about is that, well, I think I know how you do it, is actually this, yeah, so this is Dev's question actually. So once you know this, you want to get back to usual bounded cohomology. And how you do this is a bit complicated, I think, because you kind of want to apply this left adjoint, this C functor, to go in the junction between the left heart and Bornological spaces. But you have to sort of derive this. So I think you'll get some like spectral sequence comparing Bornological bounded cohomology with usual bounded cohomology, and how you compute this isn't unclear to me. So yeah, it's an easier invariant to compute, but how it relates to the classical one, there'll be some formula, or well, there'll be some spectral sequence, but how easy it is to compute, I'm not sure. I think it does agree with, so Bühler has this definition of Bornological bounded cohomology for groups. And I think this will be the same when you input, instead of X, you input like K, G of 1 or whatever. And so it does agree with things that people are interested in. But how you compare it to usual stuff, I'm not sure. So yeah, it's sort of easier to compute, but yeah.
When so when you take normal usual spectra, right, and you tensor with Q, so you do rational stable homotopy theory, then you're left with actual chain complexes, right?
Yeah.
So is there a general theorem like that says in general setting?
Yeah, if you so if you look at generally, I think if you take if I take some ring object in the heart and I look at this Eilenberg-Maclane object and I look at modules over this, this would be the category of chain complexes. It embeds fully faithfully in this category of Bornological spectra. And then if my ring happened to be enriched over Q or contain Q, then you get a fully faithful embedding. So yeah, you get an equivalence. And it'll be something like what happens usually, I guess, the map from the sphere spectrum to like the Eilenberg-Maclane spectrum of Q is sort of this homotopy monomorphism or homotopy epimorphism. So you do get the same thing, yeah. The rational theory just reduces the complexes.
Yeah, so because, I mean, so, you know, with Dev and Ralph, we have these complexes of Bornological modules, complete Bornological modules, and there's no obvious Bornology in the homology that we detect. If Dev thinks otherwise, he can correct me. But since, I mean, of course, we in addition have live in the, you can say, you force the suspension square to be the identity, right? Because we are two periodic. But since they are, since the complexes are Bornological modules over the Gaussian field, which has characteristic 0 of a DVR of a complete evaluation ring, well, maybe there is a way of thinking of this complex in your setting that will somehow enrich its homology, or, I mean, modify it in a way that its homology has some Bornology in it. But do you see any way of thinking about that?
I guess Yeah, I'm not sure. I guess the way I think about how this bounded cohomology works is that yeah, I mean the sort of complexes you start off with to compute everything, they naturally have Bornological structures. And then, okay, you can take cohomology in a couple of ways. You can either take the sort of naive cohomology, turn it to the category of Bornological spaces, and this will give you some Bornology, but the cohomology theory won't be very well behaved. Or you can take cohomology in the left heart. So I guess, yeah. Yeah, but I guess what you're saying is you have some cohomology theory, so you have these like HNs or whatever, and you want to have some Bornological structure on them. Is that right?
Yeah.
Yeah. Okay.
Yeah. And I mean, we would like to have an idea of how to approach this from a concrete point of view that I can see what I'm doing, but maybe it's too much to ask.
Yeah, well, I mean, if you have the Bornology and they are defined over rationals, then you don't have to worry about the spectra. Complexes in Bornological spaces is then fine, or even complexes in the left heart, and that's all fine. But once you have the Bornology, yeah, Bornology plus rational, you don't have to worry about spectra.
But doesn't, I mean, in this statement that we have in this on the screen,
yeah,
isn't the right-hand side always a module over the real numbers?
Oh yeah, so yeah, okay.
Happen to have characteristics zero, right? It contain Q, right?
Yeah, in this instance, you actually, for R, you don't have to worry about spectra here actually, because what you can do is I take this discrete object and then you can kind of, I guess, apply L1. So that, if I consider simplicial sets, I apply L1 in each degree. I look at maps into, so I can work with simplicial objects or complexes here. But you can get more general bounded cohomology theories here. I can replace R by some Banach ring, which does not contain Q. So I can do it over the integers, for example.
Yeah, no, but say you do it over R. So
yeah, then,
do you have a complex for that?
Yeah. It's just a complex I'd had at the start, basically. Yeah. Yeah, I guess from here, if you unravel it here, I'll technically be working with simplicial objects, but you have some Dole-Kahn equivalents in this quasi-abelian setting, so you can pass.
Yes, simplicial is fine. So you take L1, so you have a simplicial set, you apply L1 the dimension wise.
Yeah.
And that's it.
Yeah, and then you map into R in each degree.
And then you map into it,
That gives it to you, yeah.
And if I didn't map into R, would I get homology?
So if you mapped into something not over Q or something.
No, I don't take map.
Yeah. I think you get bounded homology, yeah. Yeah.
Okay, so that's all for me. So are there any questions from someone else? Okay, I don't see any, so let me stop the recording.